Okay, so let's take a look at the second half of section 1.3. Okay, first thing we're going to look at is what's called the greatest integer function. Okay, it's a special function. Okay, and the greatest integer function is defined to be the greatest integer less than or equal to some value. It's the greatest integer that you can think of that's less than or equal to some value. And the symbol for it. Okay, in our book you might see this kind of double bracket symbol. On the calculator, you'll see it as capital INT, X. Okay, let's try an example. What's the greatest integer you can think of that's less than or equal to 2? What's the greatest integer that's less than or equal to 2? Yeah, Corey? Oh, I'm sorry, Andrew.
Would be 1.
Is there any integer that's bigger than that, that's less than or equal to 2?
2.
2. 2 is the biggest integer that's less than or equal to 2. How about 1.3? 1. Okay. 1 is the biggest integer that's less than or equal to 1.3. How about 1.5? Still 1. How about 1.8? 1. Okay. It's the biggest integer you can think of that's less than or equal to the number that you have. Okay, let's take a look at what it looks like when you graph it. Okay, so to graph it, you go to your y equals, press math, go over to number, and it's the 5th option down, integer. Okay, make sure you put in your variable, close your parenthesis, and I would try zoom 6. Okay, start with that. Okay, what does it look like when you graph it? What do you see? Anyone describe what you see on the screen when you graph that?
How do you get to integer?
How do you get to integer? Math, number, 5th option down.
Thank you.
You're welcome. Yep, some people said, what do they say it looks like?
Looks like stairs.
Yeah, it kind of looks like a set of stairs. I got to fix my zoom. See, if you have a bad zoom, this is what it'll look like. That's what it should look like. Now, is anybody's stairs connected? They connected each step. Okay, the calculator, a lot of times it doesn't like to draw things that are not connected. Okay, this is discontinuous, meaning if you're going to sketch it on paper, you've got to pick up your pencil to sketch it. If you have an older calculator, the older calculators, they don't have this feature of detecting the asymptotes, and when you graph it, it looks like that. Notice it did it a little faster, but it tries to connect everything. That's not how it should look. Okay, the way it looked before is what it should look like. Okay, and since it kind of looks like a set of stairs or steps, they also call it a step function. It's also known as a step function. Okay, and if we were going to sketch it properly, we have to be careful with the endpoints of each step. Okay, do you include the endpoint of the step, or don't you include it? Well, let's say let me zoom in a little bit here. Okay, if you're at like 0.5, the greatest integer less than or equal to 0.5 is 0. 0.6, it's still 0. 0.7, 0.8, 0.9, up to 0.99999, it's still 0. Then when you get to 1, the greatest integer less than or equal to 1, it's not 0. So we don't include that endpoint. We jump up to the next step, and we include that. Okay. And then 1.1, 1.2, all the way up to 1.9 repeating. The greatest integer less than or equal to 1.9 is 1.9. Sorry, 1. And then when you get to 2, you don't include the endpoint. You jump up to the next step, jump up to 2. So any questions about these open and closed circles? About jumping up? Sometimes you see this kind of thing with like postage. If your package is between, I'm just going to make it up, 1 ounce and 1.9 ounces, it doesn't matter. You pay the same price. 1.2 ounces, 1.5, 1.9, doesn't matter. Once you go to 2 ounces, then you jump up to the next postage category. Okay, so sometimes you might be able to visualize that kind of thing at like a post office. So we already found a complete graph. Just the standard window works fine. So you could write down x min for negative 10, x max positive 10, so on. Okay, and I want to know the domain and range. Okay, so remember, the domain is what you plug in. So it's what values are we allowed to plug in for x? Okay, what do you think? What's the domain here? What can you find the greatest integer of? Or if you're confused, think about it, is there anything that I couldn't plug into the function? Yeah?
Let's say all real numbers.
Yeah, you can, all real numbers. You can find, for any number you name to me, I can tell you what the integer is that's less than it. Anything. The greatest integer that's less than it. All real numbers. Or if you're used to seeing this symbol, that's the symbol for all real numbers. I'll use that later on. How about the range? The range is what you get for y values. What kind of values do you get out of the greatest integer function? Yeah, Andrew?
Integers.
Just integers. Good. All integers. Okay, when you plug something into the greatest integer function, you would never get an answer of 5.6. Greatest integer function only returns integer values. That's why if you zoom in, oops, there's nothing between steps. You can get a y value of 0, or if you trace over far enough, keep going, you get a y value of 1, but there's nothing between 0 and 1. This function only returns integers for y values. Okay, let's graph this and see if we can find the domain and range. Okay, this is a polynomial. It's a degree 3 polynomial. Does anybody remember how many times a degree 3 polynomial can turn? Yeah, 2. It's 1 less than the degree. So it's an odd degree polynomial. So I guarantee you it's basically going to look something like this or something like that. One of those two basic shapes. And we'll learn more about how to do what I just did in a little bit. Okay, so 16x minus x cubed. Start with zoom 6, but I don't think that's going to be a good window. Okay, it's definitely doing some turning, but I can't see it. So what I'm going to do is I'm going to zoom out. Okay, Matthias, which axis do I need to zoom out on, the x or the y?
Y.
Yeah, I'm not seeing high and low enough. Okay, so let's try negative 40 to 40. And if that's still not good, we'll zoom out a little more. No, that's good. That's a good good window. Okay, so first the domain. Okay, the domain is basically how far left and right this graph is going to go. Or if you want to think of it algebraically, what values are you allowed to plug in for x here? What about Brad? What values could you plug in for x here? Yeah, all real numbers. Any value that you plug in, you have to be able to cube it. You can cube anything you want. Any value you plug in, you've got to be able to multiply it by 16. You can multiply anything by 16. The only time you run into a problem with the domains is if you have a fraction with a variable on the bottom, or you have a square root. Okay. And how about the range? How about Shannon? How high and low is this graph going to go? Yeah, it's going to keep going forever. If you're not sure, try a value like 10 for x. Watch what happens when you plug in 10. It's going to be way down. Just try 10. When you plug in 10, you're at negative 840. Right? So this graph is just going to go way down. And the other end, if you tried negative 10, it'd be way up. Okay, so this graph goes up and down forever. In fact, this is the same pattern with any odd polynomial. Any odd degree polynomial, this is always the domain, that's always the range. So you could change this exponent to a 5, a 7. You could throw some other stuff in there. As long as the degree of the polynomial is odd, that's always the answer. Okay, next problem. Okay, it says we've got a swimming pool that has dimensions of 30 feet by 50 feet. We're going to put a sidewalk in around the swimming pool, uniform width all the way around the pool. Area of the sidewalk is going to be 600 square feet. I want to know what the width of the sidewalk is going to be. Okay, first day we talked about different strategies for solving problems. What do you think this kind of problem would be? It would be really good to do before we even set up an equation. Yeah?
Figure out what is necessary to use, right?
Figure out what's necessary to use?
Yeah.
Yeah? So do you think there's some information here that might be unnecessary? Is that what you mean?
Yeah. Maybe.
Well, let's see as we go through it. I think we're going to need most of what's here. I think we're going to need most of that. But what could be a better way to organize all this rather than the way it's here?
Draw a picture.
Yeah, really, this is the kind of problem we definitely want a picture to try to visualize what's happening. All right, so first thing is let's make rectangular. Okay, so here's our pool. And our pool is 30 feet by 50 feet. We'll shade that in blue. That's the pool. Around the pool, we're going to have a sidewalk. So the sidewalk is going to be uniform width, best I can, all the way around the pool. And it tells us the width is x. X from there to there, and x from there to there. Okay, any questions so far? Okay, what else do I know? Just by looking at this picture, using simple geometry, they didn't give me this, but I can find it really, really quick. So they gave me the dimensions of the pool, area of the sidewalk. But there's one other thing I know here just because of the dimensions they gave me. Yeah? Yeah, I know the area of the pool. Hey, Graham, just make sure everybody knows. How do you find the area of a rectangle? Yep, length times width. All right. So we got 50 times 30. Okay, that's 1,500 square feet. Okay, that's good. We're going to use that somehow. Any thoughts what I can do next? I'll give you a hint. The next thing I want to do is find the area of this big rectangle. What's... Yeah, that's what's going to go on the other side. We're going to use that too, the 2100. Yep, that's important. How long is that side in red? Yeah, Tom?
50 plus 2x.
Good. It's 50 plus x, so 50 plus 2x. And then Tom, could you tell me that side in blue?
30 plus 2x.
30 plus x plus x. Yep. And now I'm going to set up a formula to find the area of this big rectangle, just doing length times width. So there's my length. There's my width. And now, Graham, how did you find that total area? What did you add together?
I added together the area of the sidewalk plus the area of the pool.
Yep. If you take the area of the sidewalk plus the area of the pool and add them up, you'll get that expression we have on the left-hand side. Well, we already know the area of the sidewalk and the pool. Okay, area of the sidewalk is 600. What was the area of the pool? 1,500? Yeah, 1,500. And I'm going to FOIL out what's on the left. So I got 1,500 plus 100x plus 60x plus 4x squared. What could I do before I really start to solve this? There's something here I could cancel out because it's on both sides.
1,500.
Yeah, if you subtract 1,500 from both sides, that's gone. You don't have to do it that way, but it makes it a little easier. Next thing is I'm going to write the left-hand side in descending order. And this is going to be a quadratic equation. So what do you think we want to do with this 600? Yeah, we want to subtract it and move it to the other side. Anytime you're solving a quadratic, you always want to get it equal to 0. One more thing I can do before I even try to solve it. And by trying, we could try factoring or quadratic formula or graph it. But there's something I could do here to make it numbers a little smaller.
Can you divide everything by 4?
Yep, divide everything by 4. Okay, so that leaves me with x squared. Yep, plus 40x minus 150. Now, I'll tell you it doesn't factor. Okay, so if you tried to, do this thing, doesn't factor very nicely. So what did I say the other way you could do it besides factor? Quadratic formula. Okay. How about Madison? What would A be in this case? 1. And Heaven, B? $40, yep. And C, that would be negative 150. Okay. Now you'd have to plug all that into your quadratic formula, which I'm just going to write down so you have it. You know what? Let me do it without the numbers. Negative B plus or minus. Anybody remember what goes under here? Graham? Yeah.
Minus 4ac.
And the bottom?
2a.
2a. So there's your quadratic formula. We're going to go over that more in depth later. So you could plug all these numbers in, simplify, you get the answer. I'm going to show you how to do it on the calculator. So let me show you how we can do this on the calculator. Okay. Type this into y1. Okay. X squared plus 40x minus 150. X squared plus 40x minus 150. Right, and yeah, go ahead, Greg.
Can you come here for a second? My
Yep.
calculator always gives us like a range of numbers for X max.
Zoom 6. Zoom 6 will always reset your window to negative 10 to 10 and negative 10 to 10. Zoom 6. All right, so I'm going to do zoom 6. Now, I'm not saying that's going to be a good window, but it's actually probably going to work for what we need. All right, so this is a parabola. It's a U shape. Okay, so this is coming down. It's probably coming back up somewhere else. Okay, probably way on the negative part of the x-axis. Now, x represents the width of the sidewalk. Do I care about a negative answer for x? No. In this case, it's a word problem. I don't care about the negative answer for x. I can see the positive answer. So I'm just going to go with this. Now, I'm trying to find where this graph hits 0. Okay? What value would you have to plug in for x? So you do all this arithmetic out, and you get 0 for y. Does anybody remember what you call that, the name of where a graph crosses an axis? Yeah? Yeah, bless you. An intercept. Very good. So what we're trying to find here is a x-intercept. Where does it cross the x-axis? Well, press second, calc, and we haven't done this one yet. It's a 0. Okay, we're trying to find what value is going to make this graph 0. Second option. Okay, left bound means you need to pick a point that's to the left of your 0. Okay, so it's going to, if you're looking for your arrow, okay, I can see my x is at negative 1, so I'm way off. I need to start heading back up till I get to about 3 on my x-axis. All of a sudden, I'll see the value. There it is. Pop up on the screen. Okay, it's so steep that it kind of jumps quick. So as long as you pick a value to the left, which we are, we're just slightly to the left, hit enter. Okay, go to the right. It doesn't matter as long as y is positive. Go to the right. And it put these two little blue triangles. What that means is it's going to look for a 0 in this area here. You just told it where to look. And then the guess, that's not really important, but just get as close as you can. And the answer is about 3.45. Anybody else get that on the calculator? Good, good. You could have done exactly the same thing with the quadratic formula, except that would have given you the exact answer. This doesn't. Okay, so that's kind of the one downside of the calculator. You don't get the exact answer, but if you don't need it, who cares? Is everyone familiar with this symbol? It means about. Remember, x was not an area, so it should not be square feet. It was the width of the sidewalk. Okay, any questions on that? One thing you cannot do, somebody asked me, is could you do an intercept? Could you calculate, use second calc intersect? And I said no. Okay, an intersect is only for where two graphs cross each other. If you did something like this, I just drew a line in right on the x-axis. Now I could do an intersect and get the same answer. Okay? But if all you have is a graph and you want to know where it crosses an axis, you want to use root, okay? Or 0. All right. Any questions on that? So here's an equation you might see in physics. How many people are in physics right now? A couple. Okay, so you might see this. Basically, projectile motion is if somebody's standing on the ground. They throw an object and kind of makes that pattern. There's a couple things that are important in this formula. Okay, one is initial velocity. That's how fast you throw it. And initial height. Okay, initial height would come into play if, say, you were standing on top of a building and you throw an object off like that. If you read the problem and it says ground level, that means the initial height is 0. This negative 16, does anybody know where this comes from? Has to do with physics. It's the acceleration, well, it has to do with the acceleration due to gravity. If you're working in feet and seconds. I'm going to guess in physics, you're probably going to work in metric. So you'll probably use meters per second. So that number would be a little different. Okay, but make sure you have that copied down. Projectile motion formula. And this, again, approximates motion as you throw something due to gravity pulling it down. Okay, assuming that once you throw it, there's no other force really propelling the object. So like like a missile or something, it might be launched, but then it might have an engine on it that keeps it going. This is just you throw it and gravity takes over. Okay, so let's try an example. Does everyone have the formula? So we've got a model rocket. It's going to be shot straight up from ground level. So what does that tell you? Ground level. Yeah.
Tells you the initial height. You don't need to use it.
Yeah, we're not going to use the initial height in this problem. An initial velocity of 64 feet per second. Okay, a couple things I want to know. First, I want to know when the rocket is going to be above 50 feet. And keep in mind, that's probably going to be an interval of time. Okay, the rocket's going to be going up, and then at some point, it's going to be above 50 feet. It's going to stay above 50 feet. And then at some point, it'll drop back down. So it'll probably be between a certain time it's above 50 feet. And then I want to know what's the highest that the rocket reaches, and at what time does it reach its maximum. All right, so let's start with part A. What do you think? What do you think the first thing I should do is, before I even think about like solving things or plugging things in? I don't even have anything to plug in. So what should I do first? All right. So before we can try to even solve it, we got to come up with something to solve. So what could I use for an equation? What would I plug in? How about Brad? What do you think?
Plug in the initial velocity.
Yeah, where would you plug in the initial velocity for what?
The V.
Yep, v sub 0. And for initial height, Graham told us we can plug in what?
0.
0. So what would this equation look like if you do exactly what you just said?
Negative 16t squared plus 64 sub t.
Just t. Yep, because you've already taken care of that v sub 0. So 64t. Anything on the left?
S of t.
S of t. Good. So here's your height of the rocket as a function of time. Okay, and now, Matthias, what could I do with this equation?
Solve it.
Okay, we could actually plug in 50 on the left-hand side, and then you'd have a quadratic equation. You'd subtract it, bring it to the other side, maybe try to factor it. Use quadratic formula, you'd come up with 2 values for t. What else could we do if we don't want to use quadratic formula?
Do it on the calculator.
Yeah, let's do it on the calculator. Okay, so I want you to graph negative 16. Remember, you have to use x on the calculator. So negative 16x squared plus 64x. Now the thing is, we don't know how high it's going to go. We don't know how long it's in the air for. So let's just take a guess at our window. I know I'm not looking at negative time. I'm going to say it's in the air maybe less than 8 seconds. I know it's not going to go below ground. And let's say it goes maybe no higher than 100 feet. So remember, x is your time. Y is your height. Don't worry about anything else. Okay, hit graph. Okay, so that seems pretty good. There's the path of our rocket, and I want to know where it's above 50 feet. Okay, so what I'm going to do is I'm going to put a line in at 50. And now everywhere in blue that's above that line, that's where the rocket is above 50 feet. So how can I find those 2 time values? Yeah.
Trace.
Okay, you could try to trace and you might get close. How can we do it exact? Or as exact as we can do on the calculator?
Table.
Good guess. Table we use for a lot of stuff, but table won't help here exactly.
Intercept.
Yeah. Second, calc, intersect. Okay. Here, the guess matters. Wherever you put your guess, that's the intersection point it's going to give you. Okay, so I hit enter on each curve. Now it's asking for a guess. I'm going to do the one on the right. If somebody else can just keep moving over and do the one on the left. So this rocket is going to, after 2.93 seconds, it's coming back down. It's going to go below 50 feet. Or 2.94. So the time has to be less than 2.94 seconds. Can't go past that, otherwise it drops below. And what about this first point? Can we get that? Yeah, go ahead, Corey.
1.064.
Okay, it's about 1.06. So if you pick a time greater than 1.06 seconds and smaller than 2.94, it'll be above 50 feet. What would be the domain for the time on this? What values would you be allowed to pick based on what you can see there? Well, what don't we want to happen to the rocket, or what's impossible? The rocket can't do this. Can't go underground. Okay, we're going to assume it stays doesn't go any lower than 0 feet. So what would be the highest time value you think you could hit before it would hit the ground? Think about heaven. See where it looks like it's going to hit the x-axis? So at 0, it hits the x-axis. That's when it's taking off. And where else? Looks pretty close to what? Four. Okay, probably after 4 seconds, it looks like it's going to hit. It hits the ground at 4 seconds. So you wouldn't want to look at any time beyond 4 seconds, because if you do, now it's negative. And that doesn't make sense in this problem. Right, so we're only looking at times between 0 and 4 seconds. Okay, last part for the rocket question, I want to know the maximum height. Well, on the calculator, we have a feature built in that we can find that. Just go second, calc. It's the 4th option down, maximum. Okay, you need to make sure that you are on the blue curve. If you have both of them drawn and you're on the red one, hit up or down. That'll move you to the blue one. Okay, pick a point somewhere to the left of the maximum. Pick a point to the right. Now the calculator is going to look in that area. Okay, and you see 2.00000012. You might also see 1.9999999. Anybody get that? Yeah. We're going to round it off to what number you think? 2. So at 2 seconds, what's the maximum height? 64 feet. Okay, so at 2 seconds, the rocket hits a max height. Of 64 feet. Okay, so that's how you can use second calc maximum, okay, to find a max. I think we used it the other day maybe to find a minimum. I'm not sure.
What?
And last thing in section 1.3 is what's called a piecewise function. Okay, basically, what a piecewise function is it's 2 different functions graphed together at the same time. As you're copying it down, I'll show you an example. So usually, like in Algebra 1, when you sketch a picture of something, they give you one thing, and you plug x values in, and you make plots and points, and you sketch it. Well, in a piecewise function, you can have 2 or more functions. And which one you use depends on what your x value is. Okay, so it's kind of like if, in this one, if I said, all right, if you give me an x value less than 1, I want you to plug it into this formula. If you give me an x value that's greater than or equal to 1, I want you to use a different formula. So you're using a different formula to find y, depending on what x is. It doesn't have to be less than 1 or more than 1. It could be less than 10 and more than 10. You can do it any way you want. But what we're really going to look at is how do you type this in? Okay, the way you type in a piecewise defined function on the calculator is you need to put it in parentheses. Yeah?
Can you go up a little bit? Thank you.
Right, so what I'm going to do is I'm going to type in 3 minus x squared in parentheses, whole thing. I'm going to type that in on y1. If you got anything else, you can get rid of it. Okay. And then after it, I need to type in where I want it to graph this. So I want it to graph this, but I only want it to graph this for x is less than 1. I don't want it to use this when x is not less than 1. I'm going to use something else. So in parentheses, I'm going to type in that condition, x less than 1. Okay, so put another parenthesis, put x, and then you press second math. That's how you get to your inequality symbols. And the fifth one down is less than 1. Okay, now do the same thing. Type in the second one. Put it in parentheses. X cubed minus 4x. And that one's when x is greater than or equal to 1. So what we're going to see is basically two different graphs at the same time. Yeah?
How do you get to the less than?
You press second, math, and then you'll see all your inequality symbols. Okay, for this one, just do a standard window. Zoom 6, I think, is going to work fine. Okay, so notice this one just stopped. It went up a while and it just stopped. Ignore what you see on the x-axis. That shouldn't be there, but the calculator doesn't know how to handle it. Right, so up to 1, we're using this function in blue. And then all of a sudden, when we go greater than or equal to 1, it switches to the function in red. Okay, so that's a piecewise defined function.
I just have it for one.
Yep, and you put everything in parentheses just like that.
I didn't. Okay, never mind.
Graham?
I won't let me do it.
All right, you got to type just like that?
Yeah. Sure.
Yep, it says whenever you see error window range, I'm not even going to look yet, but I'm going to guess his maximum is less than the minimum. So, yep, you got your x max and min both at 0. So do a zoom 6, and it should look okay. All right, now if we were sketching this on paper, we'd have to be a little careful how we do it. When we go up to 1, we are not including the endpoint of the top one. It's strictly less than. On the other one, it's greater than or equal. Oops. So that's what it should look like if we were graphing it on paper. Don't include the endpoint on the first one because it's just a less than. This has the equal to on the second graph. So that's why I filled that in.
When I type mine in, it's like doing this weird thing. So like, I put it on the ground.
Yeah, I think you're okay. It's just because you didn't finish filling out that thing. Okay, again, ignore what's on the x-axis. These colors shouldn't be here. This is what the graph should look like. Right? So I just want to make sure people know how to type in a piecewise function. Any question on typing in a piecewise function? All right. So this is the last part. I said I'm going to go through kind of quickly. It's on slope, y equals mx plus b, parallel, perpendicular. I think you guys know that pretty well. Okay. What do the m and the b stand for in this equation? Which one's slope?
Okay.
Good. And B? What's that? Y-intercept. Okay, if you already know that, you don't have to write it down. Okay, so our book talks about a linear function. Basically, a linear function is in this form, y equals mx plus b. And specifically, it's called a linear function. M and b can be any real number. Okay, I used this symbol earlier. This means element of. So m and b are elements of the real numbers. And specifically, if it's a linear function, the book mentions the slope not equal to 0. Sorry, just say not equal to 0. So m and b can be anything you want, except we're not going to let m equal 0, because if you do that, you get a constant function. You get a horizontal line. Okay, we've been graphing constant functions on the calculator to find intersects. Okay, so this problem, it gives you some data, and it basically wants you to find a line that would model this situation. A house was purchased 10 years ago for $60,000. Now it's worth $85,000. Assume that the value of the house has gone up linearly. The value has gone up linearly. Find an equation that models this data. Well, these points, or these values, are kind of like an ordered pair. Okay? You first purchased the house, it was worth $60,000. What value do we usually use to represent like the first, like right at the beginning? At the very beginning, it was worth $60,000. Yeah, 0. After 0 years, it was worth $60,000. After 10 years, how much was the house worth? $85,000. All right, so basically what we can use is our formula for slope. This is like x1, y1, x2, y2. We can plug it in, and we can find the slope. Okay, so that's 85,000 minus 60,000. It's y2 minus y1 over 10 minus 0. It's 25,000. Divide by 10 is how much? 2,500. Good. So there's my slope. And my y-intercept, 60,000. That's where it would cross the y-axis. So if I wanted the equation of this, the value for this house, 2,500x plus 60,000. Now, if they wanted me to find when the house was worth 71,250, where would I plug that in? For x or for y? Yeah, DJ?
Y.
Yeah, you'd plug it in for y. Remember, our x's represented time, our y's represented amounts of money. So you'd plug in 71,250. And would everyone feel comfortable solving that for x? Get x by itself? Two special cases with slope. Horizontal line has a slope of 0. Vertical line, undefined. Okay, and just as a reminder, the equation of a horizontal line, we've been doing that on the calculator. It's y equals a number. Equation of a vertical line is x equals a number. You cannot graph a vertical line on the calculator. So what would be the equation of a vertical line that goes right through the, or we'll start with horizontal. What would be the equation of the horizontal line that goes through the point 2, 3. Be y equals, yeah. It's so simple, sometimes you get confused. We don't even have to use the slope formula. Okay, we don't even use it. And Corey, how about the vertical line that goes to that point? X equals 2. If you graph both those lines, they would cross at exactly the point 2, 3. Okay, how would you take this and change it into slope-intercept form? Well, you don't have to tell me step by step. The goal would be to just do what?
Get y by itself.
Yeah, we get y by itself. Okay, when you move things around, try to write it in mx plus b order. And this is how you'd write it. What's the advantage to this versus what we had before? Yeah, it's a little easier to graph. You can see the slope, you can see the intercept. Okay, so you might have to rearrange things just like that. It might work. Point slope form, that's another way to write the equation of a line. It's y minus y1 equals m times x minus x1. Okay, it's handy if you have a problem like this. Find the equation of the line that has this slope passes through this point. Well, you can do it like this. Y minus y1 equals m times x minus x1. Be careful if you plug in a negative and you're subtracting, it becomes a positive. Okay, and this is perfectly fine. Unless they want it in y-intercept form, then I'd distribute the 1/2 and plus 3, and you could get y by itself. I'd say most of the time it's a good idea to put it in y equals mx plus b. General form, don't worry about that. We're not going to use general form that much. It's basically where you get it equal to 0 and put everything on the other side. Okay, when are two lines parallel? Actually, two things have to happen. Brad? Same slope. And one other thing. Yeah? Different y-intercept. What if they had the same slope and same intercept?
The same line.
Yeah, same line. Okay, so that's when lines are parallel. How about perpendicular? Anybody remember what happens with the slopes there? Yeah?
Don't they have to have like a reciprocal and so? I mean, the slope, so one's negative, one's positive.
All right, yep, that's part of it. They are opposites. One's negative, one's positive, and they're reciprocals. Okay, so for perpendicular lines, your slopes are opposite reciprocals. Okay, so in this one, if I said, write an equation that's parallel to this line. Well, the first thing I need is the slope of this line. So I would get y by itself. Okay, by moving 3x to the other side, divide by -2. Now I know the slope. So if I want a line that's parallel to this one, just use my point slope form. Y minus y1 equals m times x minus x1. There's your equation. I just had to figure out the slope. That's all I needed. If I wanted to distribute it and then -2, I could do it. Now, if I was looking for a line that was perpendicular, what's the opposite reciprocal of 3 over 2? That's the reciprocal. -2 over 3. I would use that instead, if I wanted perpendicular. All right, and this is the last. That's the last thing. Okay, how we graph an inequality. Okay, most important thing you got to remember is when you graph an inequality, you graph it just like you're graphing a line, except if you see one of the less than or equal, greater than or equal, it's solid. If you see less than or greater than, it's dashed. And then you got to figure out what side to shade on. Use a test point. Okay, that's just the quick way to say it. I'm going to test a point. Let me show you how we do this one. Okay, first thing we have to do is graph this. So you have to get y by itself. Divide everything by 3. Right, so we get y is less than negative 2/3 x plus 4. Okay, I'm just going to graph a couple points. Oh, I'm sorry, plus 4/3. Thank you. So 4/3 is about 1.3. And then my slope says down 2, right 3. Down 2, right 3. Not perfect, but close enough. It's less than, so I use a dashed line. And then I either shade above or below. You can use a test point, or if you just remember, less than means which way, above or below? Yeah, it's below. Shade below. If you wanted to check a quick test point, you could plug in 0, see if it works. Is 0 less than positive 4/3? Yes. Because if you still have 0 here, that's wiped out. 0 is less than 4/3. So sometimes people use a test point. Sometimes they just remember less than means shade below, greater than means shade above. Okay. All right. So a lot of different stuff in that section, but I hope most of the review. Mostly. All right, so the homework on page 31, it's the last part of what you guys did over the weekend. And then page 42, that's on slope, y-intercept, and all that stuff. Take a look at that tomorrow.